Welcome back, everyone. The topic for this video is solubility. So, as usual, before we jump into the Gen Chem 2 topic on solubility, you do need to review your solubility rules from Gen Chem 1. How to create products in a balanced chemical equation, how to determine which of those, if any, are going to be soluble or a precipitate. And so this time we're going to go through one quick practice problem just to refresh your memory, but you may want to go back and review additional videos to catch up on this. So in this question, they tell us that lead 2 nitrate reacts with sodium iodide. Predict the products of the reaction, including their phases. So I think that it's best to start out by writing those two reactants. Remember that the Roman numeral 2 tells us the charge on lead, so that's going to tell us that we have Pb with a 2+ charge. And nitrate, you'll have to review your polyatomic ions, but that is NO3 with a -1 charge. And so if we want to form a compound between these two ions, then you're going to take the charges and crisscross them to form your subscripts. So that first compound in the reaction will be Pb, and parentheses around that polyatomic, NO3, and there are 2 of those nitrate ions. Now, to determine the phase for lead nitrate, that's where you're going to need your solubility table, and this is just the one that we use for this class, but there are several others out there. And we are looking typically at the anions to determine whether it's soluble or insoluble, and we're looking at nitrate as our anion. So on our table here we have nitrate, which is always soluble, and there are no known exceptions. So anytime you see a nitrate in a compound, you can go ahead and assume that that is soluble, which means that it will be aqueous in its phase. Okay, and then we have sodium iodide, so that would be sodium is Na+, because it's in the first column on the periodic table. Iodide is an I-. Again, it's a halogen, so those are going to contain a negative charge, and those are a 1-to-1 ratio, so no subscripts needed, and we get NaI as our second compound. Then we're going to look for iodide on the solubility table, so that's here. Okay, and it is soluble unless it's bound with silver, mercury, or lead, and specifically lead 2. So if we go back, it's not chemically bonded to any of those right now, and so that's also going to be soluble. Okay, now when we're forming our products, remember that you have to swap the cations, basically. So sometimes you may see a rainbow where you're bonding the outer and the inner. So that's one way, or let's see if I can erase this. Another way to think of it is to just swap those cations out. Okay, so the sodium will now be bonded to the nitrate. Again, you always have to stop and think about those charges. So if the sodium, which always has a +1 charge, is bonded with the nitrate, which has a negative charge, those are a 1-to-1 ratio, and we don't need any subscripts besides the subscript in the polyatomic, and we get NaNO3. Remember, nitrates are always soluble, so we know that that is going to be aqueous as well. And then the second product, we're going to now bond that lead, the Pb, with an iodide. And we want to assume that lead has the same charge that it started with. So remember, lead 2 is going to have a 2+ charge, and the iodide has a negative. And so we're going to drop and swap that 2 to give us PbI2. And remember, iodide was not soluble. One of the exceptions was when it was bonded to lead. So we're going to say that that is insoluble, and so it's going to form a solid, and therefore that is our precipitate. And if you needed to take this a step further, you may want to try to balance this equation. We notice that we need 2 nitrates when they're bonded to the lead on the reactant side, so we would need 2 nitrates on the product side here as well, and that means we're going to have to put a 2 as a coefficient in front. Now, that 2 not only tells us that we have 2 nitrates, but we also have 2 sodiums. So we need to put a 2 in front of the sodium on the reactant side to balance those sodium ions as well. And then it should be balanced. But I think for the purposes of this chapter, the main things that you will need to be able to do are predict products and determine if those products are soluble or insoluble. Okay, so some quick definitions concerning solubility. So solubility itself is going to be the maximum concentration of a solute that can be dissolved in a solvent under specific conditions, right? So if a solution is considered to be saturated, then its solute concentration is equal to its solubility. So saturated would mean that the maximum amount of that solute has been dissolved in the liquid, and you may have some solid left over at the bottom of your container. So that's what they're showing you in the picture here. You have extra solid that's at the bottom, and the maximum amount that can be dissolved is dissolved. Unsaturated is if we have a solute concentration less than the solubility. So we could continue to add more salt past an unsaturated solution, and it would continue to dissolve. And then supersaturated, this is a special condition where we have the solute concentration exceeding its solubility. So these are special conditions where we have to heat up the solution, dissolve more solute, and then cool that solution down in order to contain more solute than what is soluble. So we'll talk more about that near the end of this section. We remember the solutes in a liquid, they could be a gas, a solid, or a liquid. So we're going to focus on gas solutes in liquid solvents first. Remember the phrase like dissolves like. So we're going to keep bringing this phrase up, but similar intermolecular forces, right, solutes with similar intermolecular forces are going to be most likely to dissolve in a solvent. What this means is that if we have a polar solvent, then polar solutes, which also have dipole-dipole forces, are going to dissolve in that solute or in that solvent. If we have a nonpolar solvent, like our gases our gasoline and our oil, nonpolar solutes are going to dissolve in nonpolar solvents. So again, like dissolves like. And with gases, the only interactions that are going to contribute are going to be our solute-solvent interactions that will energetically favor the solubility. So solute-solute gas interactions, those will not exist in a gas because they're so far apart, and so the only ones that will matter are the solute-solvent interactions. Just as a few quick examples here, oxygen gas is going to be 3 times greater than helium gas to dissolve in water, and this is because there are greater dispersion forces in that oxygen molecule, because the larger that a molecule is, the more dispersion forces that it's going to have. And oxygen gas would be 100 times less soluble than chloromethane, CHCl3, in water. And this is because oxygen gas, remember, that's nonpolar. Both of the atoms are the same. And so oxygen gas is only going to have dispersion forces. But chloromethane, CHCl3, will have dipole-dipole attractions because, remember, it is polar. That external hydrogen atom is different than the chlorine atoms, and so it's considered polar and will have dipole-dipole attraction to the water. And Oxygen gas is also going to be more soluble in hexane, C6H14, compared to water, again, because hexane, C6H14, is considered nonpolar. Oxygen is nonpolar as well, and so those are of similar intermolecular forces. Water has dipole-dipole and hydrogen bonding interactions because it does have that oxygen directly bonded to the hydrogen. It is a polar molecule, and so it is the least similar to oxygen, or it is less similar than the hexane, which is nonpolar. Okay, so just keep in mind, when we're looking at solubility, it's all based on these intermolecular forces. So some other factors that can affect solubility are temperature and pressure, specifically with gases. So temperature will affect the solubility of gases and solids, but pressure will only affect the solubility of gases. So as the temperature increases, the solubility of a gas is going to decrease. And the best example for this would be to look at your soda cans, right? If you take an opened soda container and set it outside in the heat, you're going to notice that your soda becomes flat. And that's because the solubility of the carbon dioxide in that can, it's going to decrease with the increase in temperature. So if you put that soda can in a fridge or in a freezer, it's going to retain that solubility of carbon dioxide gas for longer than it will outside in the heat. And the solubility of gas is going to increase with increasing pressure. And again, the best thing to think about is it's the soda bottle again, but now we're deciding whether that soda bottle is closed or open, right? If you keep your soda bottle closed, it's more likely to retain that fizz and that carbon dioxide gas, but you open that soda bottle and it's going to go flat quickly, again, because you are lowering the pressure inside that container. So Henry's law helps us describe the solubility of a gas in terms of the partial pressure of that gas. And the equation is going to be the solubility, which is represented as a capital C, equals K times the partial pressure P. And K is a proportionality constant. This is going to change depending on the gas solute, what it is dissolved in, so the solvent, and the temperature. So we're going to do a couple quick examples with Henry's law. In this first example, at 0 degrees Celsius and 1 atmosphere, as much as 0.7 grams of oxygen gas can dissolve in 1 liter of water. At 0 degrees Celsius and 4 atmosphere, how many grams of oxygen gas dissolve in 1 liter of water? Okay, so if we look at Henry's equation, we've got C equals K times P. Okay, so that capital C, remember, that is concentration. Solubility is going to be represented in concentration values, and the concentration unit that we know currently is the molarity, right? So we need to determine the molarity that we have at the conditions that they have given us. And they tell us that 0.7 grams of oxygen gas can dissolve in 1 liter of water, and molarity is equal to moles over liters. So we're going to have to convert that 0.7 grams of oxygen gas into moles. So we're going to take the 0.70 grams of O2, and oxygen is roughly 16, so if there's 2 of those, it's roughly 32 grams per mole. This is coming from the periodic table, right? We calculate the molar mass, and so 32 grams per 1 mole. We've got to divide by that molar mass so that the grams cancel out. Okay, and so we're going to take 0.7 divided by 32. And we'll keep at least 3 digits of significance until the end, even though we have 2 digits from that 0.70. So this is going to give us 0.0219 moles of oxygen gas. Okay, and they tell you that that is the amount of oxygen gas dissolved in 1 liter of water. So of course, if we take that, the moles, the 0.0219 moles, and divide that by the 1 liter of solution, we assume that the gas is not going to have any volume that matters to us. And so that gives us back the 0.0219 molarity for the concentration of O2, and that is at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. So we now have the solubility in concentration units, and we also know the pressure when we have that concentration. So that molarity will be equal to our Henry's law constant K, which we don't know yet, and then times the partial pressure, which we will assume the pressure to be 1 atmosphere. Okay, so if we have that molarity value equals K times 1 atmosphere, we can simply solve for K by dividing by 1 atmosphere on both sides. Right, and so that becomes simple. K must be equal to 0.0219 molarity per 1 atmosphere. Okay, and you'll find that K values are in molarity per atmosphere. So now they are asking how many grams of oxygen will dissolve in 1 liter of water at a new pressure of 4 atmospheres. So if we want to calculate the new concentration at the new pressure, then we can still use Henry's law constant, where the solubility will be equal to the K value that we now know of 0.0219 molarity per atmosphere times the new pressure of the system, right? And so now we're at 4 atmospheres. Atmospheres will cancel, and we will be left with the concentration. So we're going to take that value, 0.0219 times 4, keep at least 3 digits of significance, and so we get 0.0875, and that is concentration in molarity. So how many grams of oxygen will dissolve in 1 liter of water? Remember, molarity can be used as a conversion factor because it is moles per liter. So we will take the 1 liter of water, so 1 liter of solution, times our molarity, 0.0875 moles per liter, right, because molarity is moles per liter. And so that molarity is equal to the amount of moles that you have of oxygen. Okay, so a lot of this is pretty simple math because we have so many ones floating around. But this is moles of O2, and so of course the last step, if we want to find grams, would be to multiply by our molar mass of 32 grams per mole from the periodic table. Okay, and so moles cancel out. We're going to take that 0.0875 times 32, and we're going to round this to 2 sig figs, which is all our calculator is going to give us, and we get 2.8 grams of oxygen gas. Okay, one more Henry's law example. This one is a lot simpler than that first one. The Henry's law constant for carbon dioxide is 3.4 times 10 to the negative second molarity per atmosphere at a temperature of 25 degrees Celsius. Assuming ideal solution behavior, what pressure of carbon dioxide, right, so they're looking for atmospheres, is needed to maintain a carbon dioxide concentration of 0.1 molarity in a can of lemon lime soda. Okay, so we're given Henry's law constant. Remember, that is going to be our K value. And we are also given the concentration, which is our solubility. And so it looks like the only thing that we must be solving for is the pressure, right? Pressure of carbon dioxide gas. So if we want to solve for P in this equation, we just need to divide by K on both sides. So our pressure is going to be equal to our Henry's law, is going to be equal to our concentration of 0.10 molarity divided by the Henry's law constant of 3.4 times 10 to the negative second molarity per atmosphere. So our molarity value, or molarity units, will cancel out, and then 1 over the atmosphere. That will kick the atmosphere up to the top. So we will get units of atmospheres at the end. And take 0.1 divided by 3.4 times 10 to the negative second gives us, with 2 sig figs, right, because both of those values that we used were 2 sig figs, 2.9 atmospheres. Right, so Henry's law, pretty simple most of the time. Usually you're given 2 of the 3 variables and asked to solve for the third. So we looked at solutions of gases in liquids. We're going to briefly look at solutions of liquids in liquids. So remember, by definition, miscible is going to be when 2 liquids are infinitely soluble between themselves. And again, these liquids are going to have similar polarities. So for example, ethanol, sulfuric acid, ethylene glycol, all of these are polar compounds, and so they're going to be miscible in water, which is also polar. And then immiscible liquids, those are going to be ones that do not mix, and gasoline, oil, benzene, carbon tetrachloride, all of these are nonpolar liquids, and so they're going to be immiscible. They're not going to mix with water, which is a polar compound. Again, the weak attractive forces between polar and nonpolar molecules, that's not going to be strong enough to overcome the strong hydrogen bonding that occurs between water molecules. And just keep in mind, you can have partially miscible liquids. So these are the 2 extremes, where they're infinitely soluble, which is miscible, or not soluble at all, which is immiscible. But you can have partially miscible solid or partially miscible liquids as well. Okay, so we're going to go through a few examples where we look at the solubility based on intermolecular forces. So in this first example, we are looking at which of the following is more soluble in water. Okay, this is based on the carbon chain length. So if you remember from our topic on intermolecular forces, the longer the chain length gets, the more nonpolar it is, right? So all of those carbon and hydrogens, those are considered nonpolar. But then we have this OH group, this alcohol group, which makes this molecule polar. Okay, in the second compound, we have a smaller or a shorter hydrocarbon chain that is nonpolar. In comparison to that OH group that we already said was polar, right? So the more nonpolar that something gets, the less likely that it's going to be soluble in water. And so the longer the hydrocarbon chain gets, the less soluble that it's going to be in water. So longer hydrocarbon chains is less soluble in water. Okay, and so which will be more soluble in water? It will be the second option, right? The CH3CH2OH that has a shorter carbon chain, and then it has that OH group, and it's that OH group specifically that's going to make it soluble in water. Okay, and then in our second example, remember we have that carboxylic acid. Okay, and that carboxylic acid is going to contain an oxygen directly bonded to a hydrogen, and so that's going to have hydrogen bonding. But in the second compound, we've got that dimethyl ether, right? If we draw the Lewis structure out for this, you've got the carbons have 3 hydrogens attached to each of them. And then in between those carbons, you have that oxygen. Okay, so you do not have a hydrogen directly bonded to that oxygen, and so for this second compound, there's no hydrogen bonding. And remember, water, H2O, of course, it does have hydrogen bonding. Because we have those hydrogens directly bonded to the oxygens. So water is going to have hydrogen bonding, dipole-dipole, and dispersion forces. It has all 3, but its strongest force is that hydrogen bonding. And so it's going to want to dissolve things that also have hydrogen bonding. So we go back to that like dissolves like phrase. So the fact that the CH3COOH has that hydrogen bond in it is going to make it more soluble in water. Okay, so again, you're looking at the intermolecular forces, and the more similar that the intermolecular forces are to each other, the more soluble that a solute will be in that solvent. So in this example, we're looking at which of the following is going to be more soluble in oil. So remember, your gasolines, your oils, those are going to be considered to be nonpolar, right? And nonpolar compounds are only going to have dispersion. So if we're looking for a similar structure with similar intermolecular forces, we need to find things that are either nonpolar or they may have dipole-dipole interactions, but they certainly should not have hydrogen bonding. So when we look at A and we look at the 2 examples here, this example on the left, you have a carbon-oxygen bond. That oxygen is different than all of those hydrogens, and so that is going to make that molecule polar, right? Remember, most molecules are going to be polar if they have different outer atoms or if they have lone pairs on the central atom, if it's just one central atom. Okay, so we have that oxygen, which makes that compound polar, and so it's going to have both dipole-dipole and dispersion, right? But the second compound, it's all carbons and hydrogens, and so this is considered nonpolar, and it's only going to have dispersion, and it is going to be most similar to the oil, which is also nonpolar. Okay, in the second example, we've got CH3COOH. We've already seen that that oxygen directly bonded to that hydrogen means that it's going to have hydrogen bonding. Okay, and something that has hydrogen bonding, it's going to be very soluble in water, but not soluble in oil or any nonpolar solvent for that matter. And then the second compound, we've got a nitrogen with 3 methyl groups, 3 CH3s attached to it. But remember, nitrogen always has a lone pair. on the nitrogen atom, right? Nitrogens like to have 3 bonds and 1 lone pair, and so it's that lone pair on the nitrogen atom that makes it polar. Okay, so it will have dipole-dipole interactions. However, none of those hydrogens are directly bonded to that nitrogen, so you will not have hydrogen bonding, and it's going to be most similar to something that's nonpolar with only dispersion, right? We want to avoid anything that has hydrogen bonding to mix in oil. And then the last example, again, that oxygen in the center, it's going to be buried between 2 carbon atoms. And I won't draw the whole structure out, but just keep in mind there's no hydrogens directly bonded to that oxygen, and so it's only going to have dipole-dipole and dispersion forces, right? It will not have hydrogen bonding. It has dipole-dipole because the oxygen has lone pairs on that oxygen, so it is going to be considered polar, or at least slightly polar. And then the second compound, notice how there is a hydrogen directly next to that nitrogen. So this would have a carbon, and then that nitrogen will have a hydrogen coming off of it, and then the other carbon, right? And those carbons will have 3 hydrogens attached to each one of those. But what's important is that that nitrogen has a hydrogen directly bonded to it. It's got hydrogen bonding, and that's the last thing that we want in oil, okay? So it's going to be that first compound that only has dipole-dipole interactions that's more soluble in oil, right? So whichever is more soluble in oil will be less soluble in water. So I could re-ask this question and say which of the following is more soluble in water, and then all of the opposite options would be my answers there, right? Okay, we're going to briefly talk about solutions of solids and liquids. So remember, gases, the solubility is going to decrease with increasing temperature. But for solids, the solubility is going to increase with increasing temperature. And of course, a good example of this would be trying to sweeten tea, right? If you try to put sugar in a cold glass of iced tea, that sugar is not going to dissolve. But if we heat up the tea, if we boil it on a stove and then add the sugar, it's going to dissolve, right? Because solubility will increase with increasing temperature. Now this is true for most solids. It's not true for all solids. So in our graph, we can see an example of where that may not be the case occasionally, but most of the time it will. So this is how we go about preparing supersaturated solutions. So because the solubility increases with increasing temperature, we can increase the temperature of a solution and dissolve a solid until it is saturated, and then we can cool that solution down very carefully and retain that amount of solute in that solution at a lower temperature, and so it will exceed its solubility and be relatively stable. Now, a way to reverse this reaction or to cause it to precipitate out would be to add what we call a seed crystal. So we can see that in the picture down here. If you add seed crystals to that solution, it will cause it to basically precipitate out of solution. You could also agitate the solution and it will do the same thing. So last set of examples here, we're just going to look at pressure and temperature conditions for gases and for solids. So what happens to the solubility of the solute in each of the following scenarios? So let's say that we have a gas solute in a high pressure closed container. So remember that if we increase the pressure, we are going to increase the solubility of gases. Okay, so it would increase in that case. Just keep in mind that if it is a solid solute, it's not going to matter whether you increase or decrease that pressure. It's not going to affect the solubility of a solid, but it does affect the solubility of a gas. In the second example, ice is added to water before trying to dissolve sugar. So ice is of course going to cool it down. So we're going to decrease that temperature, and we are focused on sugar, which is a solid. Okay, so it does help each time to decide whether you're talking about a gas or a solid. So when we decrease the temperature for a solid solute, it's going to decrease that solubility. Okay, next example, we're talking about a gas solute again, and lowering the pressure. So if we decrease the pressure, we will decrease the solubility of the gas. And last example, oxygen gas in a pond after a hot summer day. So just keep in mind that heat can significantly affect the aquatic life in water, right? So if it gets too hot, you're going to decrease that solubility of oxygen gas and potentially suffocate your fish life. So oxygen gas, we're focused on a gas, hot summer day, so if we increase the temperature, we are going to decrease the solubility of that gas. Okay, so that ends this topic on solubility.